In the last video, we derived this approximate equation, which is an approximate equation for the total potential energy stored in a system such as this, a beam undergoing strain due to the application of forces and moments along the length of the beam. We approximated the total potential energy instead of being in terms of v and phi functions of x, in terms of the individual values of v and phi at the nodes 1 and nodes 2. And we derived this expression for the total potential energy stored in our beam. Our next step in the process is to find the minimum of this function. We want to find the v1, phi1, v2, and phi2, which result in the minimum value of this function. And I want to stress here that at this point, even though this function appears to have a lot of column and row vectors in it, it is itself a scalar function. If I plugged in numerical values for v1 and phi1 and v2 and phi2, I would get out of this function a single scalar value, which represents the total potential energy stored in this system, which again is a single value. So the way I do that, the way I find the v1, phi1, v2, and phi2 that do that are the displacements that give me the minimum amount of potential energy, is just like I did for the bar element and just like I did in my Calculus 1 courses, is I'm going to take the partial derivative of this function with respect to v1, and I will set it to 0. I will find the partial derivative of this function with respect to phi1, and I will set it to 0. I will set the partial derivative of my total potential energy with respect to v2, and I will set it equal to 0, and I will find the partial derivative of the total potential energy with respect to phi2, and I will set it to 0. So this is a scalar function. It is a one function, which gives me one value. After I take the partial derivatives with respect to my four unknowns, or my four independent variables, then I will get four equations. And of course, I'll get four equations, and I will have four unknowns. All right? Now, there's a cool thing with linear algebra, which is linear algebra takes derivatives the same way as regular algebra does. So I could go through all the minutiae of showing this to you. I'm not going to. I've actually left that as a homework assignment. But here I have a vector u and the vector u. You can think of this as a row vector u times in terms of the displacements, this is a matrix of constants, times the column vector of u. This is essentially the same thing as a constant times u squared if I was going to differentiate with respect to u. U is my displacement vector. Notice that v1, phi1, v2, and phi2 are the components of my displacement vector. So rather than write this all out in long form and then evaluate what these four partial derivatives are, I can just shorthand say, oh, when I take the derivative of u, and u is squared, and there's a 1/2 here, that squared will come down, be multiplied by this 1/2, I'll end up with 1. This u will go away because I'm going from u squared, reducing n minus 1. I'll just get u. There'll be the 1u here. Here, this is a matrix of scalars, or a vector of scalars with respect to u. U is itself just u to the first power, so the u will go away. Likewise, the u will go away here. So without going through any of the minutiae, when I take these partial derivatives, I will end up with this equation, where now I have EI b column vector times b row vector dx a single u equals the integral from 0 to L, n, which has went from a column vector to a row vector, wx, remember that's our function defining our distributed load, plus this p vector, which I previously defined in the last video as simply a vector of force applied at node 1, moment applied at node 1, force applied at node 2, force applied at node 2, moment applied at node 2. All right? Now, I didn't go through all the steps to show this to you. I'm actually left that as a homework assignment. If you're not taking this class and you've just come across this video and you want to do this yourself to prove that I can get from here to here, the way you do that is to write this equation out, the long form. Replace all the b's with the form of b I showed you in the last video. Replace all the n's with the form of n I showed you in the last video. Replace all the u's with the form of u that I showed you in the last video. Write it all out. You'll get a very, very long equation. Take 4 partial derivatives and then stack. This will result in an equation. Make that your first equation. This will result in an equation. Make that your second equation. This will result in an equation. Make it your third equation. This will result in an equation. Make that your fourth equation. Stack them all up, and you'll see that you'll get an equation that looks like this. Now, let's say on our particular example that e and I both turn out to be constants with respect to x. Then I can move them out of this integral, and I can evaluate this integral from 0 to L, b row column vector times b row vector dx. What will I get? I don't think you'll be too surprised to find that if e and I are constants and can move out of the integral, all you end up with a 4 by 4 matrix, which is the exact 4 by 4 matrix that I got when I tried to derive a solution to this problem using the direct method. If it turns out that that Wx is 0, or that there is no distributed load, then this goes to 0. I just get this integral, which I now know is a matrix, times my column vector u is equal to my external forces and moments applied at the endpoints, which will result in this linear algebra equation, the same linear algebra equation I derived with the direct method. All right? Now, I've purposely not gone into details here. I haven't filled in all the steps. We will fill in the steps on how to get from here to here. You will do that on your own as part of one of our homework assignments. In our next lecture, we will look at this problem again using Glurkin's method.